replaced by hydrogen in the end. Okay, but this part of the reaction is part of it, where the alcohol is attacked by this combination of reagents. And these two are watched very, very carefully for that reason. First of all, you can't buy Sudafed anymore unless you go to the pharmacist and ask for it, and they'll put your name down. And so if you try and buy 5 kilograms of Sudafed because you have a runny nose, you're going to get a visit from police officers. If you try and buy phosphorus over either online or by phone, the phosphorus is not going to come to your door. The people in suits are going to come to your door. Same with iodine, for the reasons that we're discussing here. There's really not a lot of need for this or this in garage chemistry. In fact, probably ought not to be doing garage chemistry at all anyway, but these two things, when they participate in these reactions, produce very noxious fumes and dangerous chemicals, which usually are a dead giveaway that something illegal is going on in some structure. People will do this in an apartment. They'll rent an apartment and try and run a meth lab in the apartment, and all of their neighbors smell stuff because of the fumes that are produced here. But this reaction is part of it here. But particularly for these two, that's a great way to get the iodine. Now, how can I get the iodo form of the alcohol we've already covered?
What was the last part?
In other words, if I don't want to buy phosphorus and iodine, but I have a legitimate reason to take an alcohol and make it into an iodide, what method could I use that we've already covered that would get past all this?
Crap. No. Don't tell us. We'll just think through it here. All right, we're done.
Remember, if I convert my alcohol into a tosyl ester and then react it with, say, potassium iodide, I can get it out. Okay, so these are reactions that have historically been done, but recognize that all of these can be done also with tosyl esters as well. Anyway, let's look at these. Here's a mechanism for the tribromo form. We've got phosphorus tribromide, and we've got our alcohol. The alcohol acts as a nucleophile. Pair of electrons going from the alcohol to form an oxygen-phosphorus bond here. Formal charge of plus goes on the oxygen here, and a bromide is displaced. The bromide, at that point, now comes back around and displaces this group as the leaving group. Once the oxygen has been attached to phosphorus, this whole thing essentially is a dibromophosphonic acid here. And it's pretty stable, and it's a good leaving group. And now my bromine, essentially in a substitution reaction, attacks the backside here. This guy comes off, and I get my bromoalkane and that leaving group. Works exactly the same way with the chlorine version. And presumably the iodo version as well. But the best way to make the chloride is to use a substance called thionyl chloride, SOCl2. Haven't we seen this before? If we haven't, now we have. Thionyl chloride looks like that. It's the acid chloride of sulfurous acid. It's a little strange looking stuff. Very, very reactive, extremely reactive. It needs to be done with particular care, because look at the products. Here's my alcohol. One of these chlorides is going to replace the OH group. The alcohol OH is going to end up as part of SO2. We're going to have HCl as a gas and our product. Now, this is a real good way to do this reaction, but it's also a very dangerous way to do the reaction. Why is it dangerous? Yeah, HCl gas is produced. Okay, and what's sulfur dioxide like? It causes allergies, sometimes anaphylactic allergies. SO2 reacts with water to form H2SO3, sulfurous acid, which which is both a fairly strong acid and an allergy causer and an oxidizer. And so, as a consequence, you need to do this a few years ago. In 236, my smartest student, bless her heart, did this reaction out on the bench without telling anybody ahead of time in large quantities. And the room was just filling up with SO2 and HCl. And fortunately, she had the presence of mind to come and tell me that something was going on. So we had to evacuate the room, and for hours. We essentially shut down the lab. I'm not encouraging anything here.
This doesn't sound bad.
No, but because of the gases that are produced here, this really needs to be done now. Okay, where the gas is going to be mixed with copious amounts of air and dumped out way up high so that there's no effect from a toxicity point of view. But excellent yields, 90+% for the chlorinated version. So typically when we try and make the chlorinated version of the alcohol, this is the reaction that's used. Here's the mechanism. It's kind of, again, our slides are somewhat cut off here, but here's our alcohol. Our alcohol, as it acting as a nucleophile, attacks sulfur. And I get an OS covalent bond here. And now this sulfur is going to release one of these four things attached to it. The best leading group is one of the chlorides. And so the chloride comes off, and I get this form right here. Chloride takes off hydrogen, and I get this chlorosulfide ester. This is still very reactive, by the way, because this is an acid chloride here. Now, at this point, this thing undergoes some rearrangement reactions. Okay, so the pair of electrons that are used to form the carbon-oxygen bond here, kind of hard to see, actually go to the oxygen, giving it a negative charge, leaving the carbon partially or positively charged. This negative ion remains paired with this positive ion. We call it an ion pair. It's a complicated mechanism, you can see. Then a pair of electrons between the chlorine and sulfur, which is fairly reactive, comes over here to form a carbon-chlorine bond and SO2. HCl is generated in this step, SO2 in this step. Now, this recognized for testing purposes, I don't expect you to write mechanisms like this on exams. I may expect you to make some comments about a reaction with respect to mechanistic considerations on a quiz, but you can always look at the book and your slides and so forth. Organic chemistry, as you've surmised at this point, is very mechanistic centered. And what's the value of mechanisms?
Well, you don't have it memorized.
It's more than just sort of muscle flexing in an academic way for an organic chemist. If I know how the reaction's proceeding, I often know how to make it work better, because I know the conditions that are prevalent in various steps. I might be able to add solvents or other additives that may facilitate some of the steps and make them run better. And that's really the big reason for understanding mechanisms. And so you're going to see, really for the rest of the semester, lots of mechanisms placed on the slides for your edification and your excitement. But recognize that they're not something that I'm going to put routinely on tests. I did that first, I can't, on a multiple choice test. But recognize that I do expect you to understand what's going on, even if you don't have every blessed mechanism memorized and under control. Does that make sense? Okay.
Yeah, it seems like we'll forget most of them, but like it seems like a lot of them have to do with charge. Whereas we're creating, positive here, we're like, oh, that's slightly positive, so it's probably going to attack there.
It does.
So we can cut, right?
What you learned in 235, where we talked about electrophiles and nucleophiles and Lewis acids and Lewis bases, still apply. The same kinds of things drive mechanisms. There's a positive center and a negative center that are attracted to one another, and bonds form as a consequence. Other bonds break. And you should be able to, at this point in your careers, you should be able to look at these mechanisms and say, yeah, I can see why that's going. Now, some of them are kind of odd looking like this. Who would have thought that this iron pair would form here? But there's evidence for that. They're actually, when they're studying these kind of mechanisms, there are elaborate instrumentation techniques and chemical techniques that allow them to actually say, we've got evidence that this is in fact exactly what happens. Now, that doesn't mean that some refinement will take place, some won't take place later on, but they've got pretty good evidence to indicate that this is how it occurs.
Is that why it's, I notice whenever there's like an intense mechanism, they put their little copyright up there. Is that because they think it's that, and so they're like, hey, this is what we think, or is it their?
It would be nice if it were that sublime.
It's not, okay.
What that is it's some artist that works for Prentice Hall
So it's for the presentation of the mechanism?
wants their work protected.
Okay.
It has nothing to do with the intelligence going
Okay.
on here.
That's what I'm
It's somebody's artwork that's being copyrighted.
Okay.
Okay. Now, other reactions that alcohol's going to undergo, dehydration. Dehydration reactions produce alkenes. The commonly used acid that drives dehydration is sulfuric acid. Let me ask you a thinking question. Why wouldn't I use HCl to do a dehydration reaction? Knowing what you know, having been here the last 20 minutes. Yeah, HCl will react. The protonation takes place just like it does with sulfuric acid, but chloride can come in as a nucleophile, and I get substitution rather than elimination. The hydrogen sulfate that's present with sulfuric acid is not a good nucleophile. And so I protonate the alcohol with sulfuric acid, but the hydrogen sulfate, no interest in the carbon at all. Okay, and so that's the reason. Phosphoric acid the same way. So these reactions require that kind of polyatomic acid, like nitric, well not nitric so much, but sulfuric acid and phosphoric acid for catalysis. Whereas if I tried to do this with HBr, I wouldn't get elimination, I'd get some substitution instead. Does that make sense? Now, interestingly, when we do eliminations with this type of reaction, some downsides. I have a carbocation intermediate, which means, unfortunately, under certain circumstances, rearrangements. We should expect the Sites F product. What's a Sites F product?
Most substitute?
Yeah, most substituted alkene is going to form. It's going to be the favored product, or most likely product. I do have a competition reaction. Okay, one of the competitions that can take place doesn't form an alkene, but I get an ether. Okay, an ether is a carbon-oxygen-carbon pattern. And actually I eliminate, this will pop up in chapter 14, but if I take CH3CH2OH, ethanol, and H2SO4, and moderate heat, we would expect to get ethene as one product, but a product that we also get is this. Diethyl ether. And notice that this is a dehydration reaction also. If I take a hydrogen off one alcohol and an OH off the other, I get water. And so this is being called in the slide a bimolecular dehydration. Two molecules lose a molecule of water as they become linked together. This reaction is in competition with the elimination reaction for the alkene. And what it says out there is important. At lower temperatures, ether is favored. At higher temperatures, the alkene is favored. And so even though we have this competition taking place, we can push the equilibrium and push the product distribution our direction by controlling temperature. So far, so good? Here's an example of a dehydration reaction. I believe you do one of these in the laboratory, something we didn't anticipate. Actually, you did this in